Good evening, everyone. So, with, it's my pleasure to welcome our eminent speaker of session 12, Mr. Navaneethakrishnan, Senior Application Engineer, Entuple Technologies, Bangalore, to deliver the session on the topic ASIC design and implementation of RISC-based processor using Cadence tools. My heartfelt gratitude for accepting our invitation to share your expertise among us amidst your busy schedule, sir. Thank you so much, sir.
Thank you, ma'am.
Now I request Ms. Srinidhi to introduce the speaker. Over to Srinidhi.
Good afternoon, everyone. It gives me great pleasure to introduce our esteemed speaker, Mr.V.Navaneethakrishnan, who is currently serving as a senior application engineer at Entuple Technologies Private Limited, Bangalore. Mr. Navaneethakrishnan completed his ME in real estate design from KSR College of Technology, Tiruchengodu in 2011 and earned his BE degree from Jairam College of Engineering and Technology, Thurayur in 2007. He also completed a real estate design certification course from Pune University in 2008, strengthening his expertise in semiconductor design. He began his professional journey as a real estate trainer at Axel Technologies from 2008 to 2009, and since then has accumulated over 10 years of teaching experience in the field of real estate design and implementation. Mr. Navaneetha Krishnan has also contributed to research through his publication titled Low Power Encoder for Flash ADC Architecture, which was presented at the IEEE International Conference on Computing for Sustainable Global Development in New Delhi. With a strong foundation in both academic and industrial domains and hands-on experience with Cadence tools, he brings deep insights into ASIC design and RSSCV processor implementation. We honored to have him today with us to share his expertise and experiences. I warmly welcome you, sir. The session is over to you. Thank you, sir.
Thank you, ma'am. Thank you for the introduction. I hope my voice is audible, ma'am.
Yes, sir. Loud and clear.
Okay, thank you. Yes. Yeah. Good evening, participants. Good afternoon. So first of all, thank you for inviting me as part of this online FTP. Can you able to see my screen?
Not yet, sir.
Check it out, ma'am.
Yeah. Now it's visible, sir.
Yeah. Okay. And presentation is clear, ma'am.
Yes, sir. Slides are moving.
Slides are moving. Okay, thank you. Okay, I think hope we have a good session. I think almost we are almost at the ending stage. So as of now, I'm going to give a not going to give an entire in detailed about the theory sessions. So today I'm going to focus on the tool based. So actually, the previous session, I think our execution manager Shiv Prasad have given a detailed view on Cadence tools introduction also, along with his research topic. And along with for me, ASIC design and implementation of RISC-V based processor. That's what the topic today. So quickly we'll have a review about the RISC-V processor design, what we have designed. So what are the options are there that we can see, and after that straightly we'll go to the implementation, the tools demo session. So the demo session consists of the complete semi-custom design flow. So the semi-custom design flow starts with the design specification. It will end with the GDS file. That was that flow. Just once the flow has started, I'll open the flow and we can see further. And The starts with the design code and design that is where simulation, functional simulation, then our logic synthesis, then physical synthesis, then that is our physical design, and finally we have an we are going to see an STA and the design process, that is a sign off process. Then finally you will have a GDS2 netlist. So what are the different tools are there and how these tools are used for designing these type of ICs. That's what today's agenda. So let me go to this topic. Been able to see this. Okay. Sorry. Yeah. So, RISC-V processor, before entering to that, right? Processor, right now, wherever if you see any type of micro, that is our electronics based gadgets, it is controlled by the processor, right? So the processor is starting with the x86 processor and the microprocessor it is started, and right now we are landed in high end of personal computers and the laptops. And how it is the revolution, it is the revolution is a very long way. And anyhow, in India our semiconductor boom will be in the next decade is our semiconductor, and AI is the main domain. Okay, so this okay. So processor works for the PCs and laptop, and right now Intel, you know everyone, right? Intel has the largest semiconductor in the world, that is producing larger number of personal computers and laptops. And compare with your x86 microprocessors and x86 process and the now microprocessors, Intel's processor or any processor if you take, they followed with the Moore's law, right? So the thousands of inventions are happened in x86 microprocessors. Okay, so thousands of inventions from x86 processors. அவ்வளவுதான் கத்த முடியுமா? ம், கொஞ்சம் many terminologies become very buzzwords in this microprocessor. You can see this superscalars, ROB. So many parameters are there: reservation station, central windows, checkpoint repair, and WAW. Or we have many versions are there. And the fastest computer right now we are ending with the supercomputers, right? So now these are the very biggest thing, and according to this Moore's law, right? So the number of transistors on an integrated chip, that is integrated circuit IC, the every 18 months the number of transistors in an IC will get doubled. That was that Moore's law. So this Moore's law works very perfectly in late 1990s and earlier. But right now, the revolution of the doubling of the transistor will be it's getting less than 18 months. So see, after this Cortex A5 and A17, or can have a very huge explanation will be there, the numbers. So according to their right now our present world also we need a high speed of computing with the modern systems. So we need the smallest device which high operating systems, right? So the processors are the main part to take care of all these parameters, right? Then the one more processor you can see, there's ARM processor, right? ARM processor and the smartphones. After your PCs and laptops, the next generation is the smartphones. So the major shift to technology for the mass production in the smartphones. So the main thing is a power less device. It's a handhold device, right? So it's a high operating with a without any power supplies. That is external supplies. We have an inbuilt battery with a number of days of battery backup. So all these things are happened due to this revolutions and the shift from chips to IPs, right? So initially we started integrating ICs, that is we call it as a chips, right? Now we are moving to chips to integrated, that is your intellectual properties. So every application we have developed as a intellectual properties, and they are holding their own products, right? So they have their fabless companies, they are moving towards the IP generation for their upcoming advancements, right? Different business models, right? Then ARM is much more cheaper than x86. That's why in mobile phones and all we are always using with the ARM processors. So you can see here the same Moore's line is shifted to the right by 10 to 15 years, as I mentioned. So the new terminologies in microprocessors. So clock gating. So low power, wherever you go, you can see low power technique. So dynamic frequency, voltage scaling, power domains, and power managements, right? So all these related to your power, that is your low power activities. And the race is the microprocessor with enough performance and the long battery life. Now, so according to this application, right, day by day requirement, our application is keep on increasing, and meanwhile the battery life also it's a matter very important parameter here, because without battery, right, battery withstand capacity, how much advancement if you are going, it will be a useless one, right? I think hope you have heard about the initial launch of Xiaomi mobile phones. Initially it was launched with this battery backup was very poor. Then later they have updated, and they have updated their firmware. Then only their battery backup has good capacity. Then only it is Xiaomi has a very famous mobile smartphones, right? So what will be the next one, right? But the smartphones become saturated now, so all we have a very high end of smartphones, everything with handy we are using. So then what is next? We'll see this smart home, auto, IoT, then A and ML. So this is the next generation, right? So no longer a single application, the shift is to many applications in a single ICs. That's what. So every other aspects of life, right? In a home, auto, wherever you go, right? Human places, wherever they are living places, all these elements are occupied by the electronic gadgets. Home automations or medical surveillance, social media, business, etc. Anywhere if you go, it will be the basic will be your IoT, artificial intelligence, and your machine learning. That was the thing. So there are many applications are working under this A and ML, right? So this RISC 5 isn't enough to learn and open to everyone. RISC 5 processor is the perfect fit, right? So RISC 5 and Moore's law, you can see the same Moore's line shifted to the right by 30 years right now after the definition. So now the new terminologies are coming behind your microprocessor will be your PPA, that is the main parameters, power, performance, and area parameters, configurable architecture, extensible architectures, then custom or instruction or extension, then early and late ALUs, early ALU and late ALUs. So the new terminologies are getting more complex than previous one. So the race is custom SOC designs with the best PPA. So custom SOC automatically semi-custom, that is a custom IC means is a full one. Now the semi-custom SOC design with the best PPA, that is your power, performance, and area will be the very important analysis, right? So the RISC 5 and RVV, that is your RISC 5 processor, RISC 5 verification background. You can see an open processor architecture is started by UC Berkeley, and compact, it will be a compact, modular, and the extensible one. So these things are is the key factor for finding out this RISC 5 processor. So RISC-V International, formerly RISC-V Foundation, we have. So formed in 2015 to govern its growth, and 400 plus members, including industry and academic, they have participated. And 2019 RISC-V Summit has over 1,000 plus attendees were attended and widely adapted in the world. And many universities adapt RISC-V as the basic ISA, that is your basic ISA for your computer architecture class, right? That is your information analysis purpose. So I'm in the process of changing the RISC-V in my next computer architecture at some other universities. And here, so the RISC-V ISA has many considerations for implementations. So negative, what is the negative and carry zero and no predictions, right? And the simple memory register models and load store, these double or multiple process will be there. Then you have, unlike your ARM processor or x86 or your Intel processor, your RISC-V processor is developed by many companies. They are developing now. Andes is one company, and Sci-Fi, Esperanto, Western Digital, and Codasep. So these are some other companies, they are developing RISC-V processors. And the advanced microprocessors, the superscaler, and has been designed by more companies. So 64-bit microprocessors are now available. Right now we are operating with 64-bit processors. Many, we have this SIMD, right? Single input and multiple DSP distributors. One is there, and the processor will be your DSP processor, and your FPU, floating point units will be there, and vector processors are there, right? Then, sorry, RISC-V superscaler, right? RISC-V superscaler microprocessors. So here we have many process cycle will be there. So common microprocessor design in is dual for ALU. So in order to low power simple design, often implemented in dual one. So the main thing is referred as your load latency tolerance to reduce the load to use. So the tolerance and what is the load you are using. So based on that load, your process architecture will be there, right? So see here a small example what it's showing.
Navneetha Krishnan, sir. Sir, you are muted, sir.
Sorry.
Navneetha, yeah.
Yeah. Is it okay, ma'am, now?
Yes, okay, sir.
Okay. Thank you, ma'am. I think someone has moved it. Right. Okay, anyhow, so these fetch one, fetch two will be there, right? These are the five main stages in the processor, right? Fetch, decode, read, operate, and your final write operations. So here we have a two cycle, that is two bubbles will be there, two cycles. The data will be idle, so that's why we call it as a two cycle bubble, and it has been overcome by no stall, right? No stall. I4 uses second ALU. So there is a other ALU will load the data instead of this loading these bubbles. Okay. So that is what the new thing we have introduced in the RISC-V processor. Okay. So the RISC-V extension. So RISC-V must grow up fast and have very basic IAC slats will be there. So it will be available at different bit sizes. Right now we are accessing with the 64-bit processors. So the next will be your 128-bit instruction set. That means completely 128-bit processor is going to come out in the market. And here you can see that it compresses 16-bit pipeline architecture, right? And here we have various parameters there. I can see M for multiply divide, A for atomic, and F for single precision, and FP we call it as single precision SP or FP, single precision. Then your double precision, that is your FP, double precision FP. Then your Q paid precision, your QP, right? So these are the new extensions for this process. Then exotic extensions for the image process, that is your .uvpls, that is your SIMD, that is your serial in multiple mode output. So V vector and J for Java and B for bit manipulation, right? So here the main thing is how the data is traveling through all the stages, right? So the extensions are defined in a foundation task group with the experts in all around groups, right? Then RISC-V vector estimation. So RISC-V vector estimation, we have the vector instruction set, agnostic vector length. So scalable data sizes, which include 2 multiplication, that is twice multiplication, and 4 times multiple data expansion arithmetic will be there. Over 300 plus vector instructions has been included for loading the data and storing the data, and for the fixed point operation and the floating point operation. We have used many instructions, over 300 plus vector application. So some of the applications of vectors, vector applications, and AML, you can see that deep learning. So deep learning is the very um, uh, developing factor in the upcoming processors. Then multimedia processing, right? The same thing we can able to see this. What's the main difference between your smartphone and the smart processing and the your latest processing, right? So multimedia processing, multimedia means graphics and image, right? Multimedia, they work on mainly on the graphics and image based portions, and the standard benchmark will be there, that is our matrix multiplication, FFT, convolution, and sort. We have many things will be there. So lossy compression will be there for JPEG and cryptographies. So this is our overall architecture for the next processor. So we have used a 5-stage pipeline architecture we have used here. So here we use branch predictions, cache operations, multiplier and dividers, and with respect to number of dollars will be there for per instruction. So that is also we are working on it. And wide data pass will be feed, right, as a data here, right. The next one we can see this, it's a forwarding vector users, and vector simulation scoreboards are there to check the outputs, proper outputs correct or not. So here data supporting with the data, different data formats are there. The standards with the INTA, that is 8 point, 64 point, or floating point, that is integer 8 and integer 64, and floating point 16 and floating point 64. So and this is our extended version, which will include binary float 16 and integer 4, right? These two things we are extending. Then vector compute instructions, so multiple functional units operating independently. So we call it as So object oriented programming, you know very well, that is WOOPs. Now it is WOOs will be there. That is what here channelable and right. Then we have this chainable, and most typically the entire architecture has been pipelined into 5 different stages. Right. Then we have this micro architecture. We have 9 independent vector functional units. So 3 fixed point unit and 3 floating point units for microprocessor architecture. Then microprocessor. Then for ALU. Then we have CAC. 3D ones. Right. So in order to issue this out of order execution, this is the main advantage we have added here. So 9 independent vectors, as I mentioned, right? ALU, MAC, and dividers units along with the mask and permutation. So 6 independent load store instructions will be there. So the main advantage over this RISC processor will be your out of order execution and completion. So one instruction is processing will be there. The other instruction cannot able to interpret for the normal processing, right? So the second processor will be idle. So the first processor become active, right? So for that, we can come to this floating point unit, right? You can open, you can see floor there, right? They have the right. Then we have this floating point unit will be there. So these are some instructions about the processors, and RISC-V is greatly adaptable and is right. So many extensions are developed in the task group, and many companies developed in RISC-V processors, high extensible and high configurable in comparison to other ICs. So the first industry RISC-V processors, vector processor. Now our own processor has started manufacturing along with that. So we have a flexible design configurations will be there to adapt with the uh, Entuple and other things, right? We are extending and we are adapt by changing this. We are changing the training time to once, right? And that we can able to do this complete RISC-V process. Okay, so this is a small introduction about the processor, right? Yeah. Okay. So we'll discuss on this later, and quickly I'll go to this hands-on as I mentioned. So the complete database will be available with me. See this. This is our Cadence complete RTL2 GDS flow. So as mentioned here, you can see it starts with the design specification, the IC specification. Then the design coding, RTL coding will be there. Then functional simulation. Then your coverage analysis, right? Functional simulation, checking the code, and the functional coverage will be there. That is code coverage and functional coverage. So this is the main metric parameter to finalize whether your verification process is over or not. We can able to finalize with the help of your coverage analysis, coverage data. Then coverage is over. Then we can convert your code into netlist, gate level netlist. That is your logic synthesis section. So after the logic synthesis section, we can
Excuse
able
me,
to
Navneet.
yeah.
Windows not showing then. Others window.
Windows not sharing.
Yeah, it's showing other window. Slider
Showing
is
up.
showing. Yeah.
Okay, okay, okay. Just a minute. Just a minute. I think sliders where it's showing now. Yeah. Screen is shown. Now, sure, now it's okay, right? The
Yes,
presentation?
yes, yes.
Yeah. Now, here the flow as mentioned, right? Specification and tail coding, functional simulation, then coverage analysis. Then finally, we are going for the gate level netlist generation, which is a logic synthesis stage. Then once the netlist is got generated, then we are moving to the test generation process to test your netlist, right? Our code is verified, but your netlist is not tested. So for to do that, we are going for the DFT process. That is our design for testability. So where we are generating the ATPJ test vectors. That is your automatic test pattern vector generation. Test vectors we are generating here. Once all these steps are completed, then we are moving to the LEC stage, logic equivalency checking. So where we are checking the RTL, that is your golden design and the revised design. The revised golden design is your RTL code, and your revised design will be your logic synthesized code. So these two things are whether it is logically equal or not. We are going to verify this with the help of your LEC tool. Then later, once it is got verified, then we can move forward for the physical design process. So physical design consists of your floor planning, power planning, then placement, clock tree synthesis, then routing. So all these five stages includes your physical design process. Then we can go for your uh, timing analysis, that is your timing side, right? So the as of now we are focus on the physical design flow, and later the STA timing concepts we are focusing, right? Whether whatever the design has been developed, whether the device can able to withstand with the timing capability, right? So which is called your static timing analysis. Then after that we are going for the gate level simulation, which is, or we call it as a post layout simulation. So we are running the same test benches with the instead of your logic network, that is your logic code. Here we are going to declare your network code, right? So that is where synthesized physical synthesized netlist code we are going to use it. So this is called your gate level simulation. So once your pre-layout simulation and your post-layout simulations are matched, then we can go for the final process called the GDS II netlist generation. All right. So this is the entire flow for the semi-custom custom design flow for the Cadence systems. Right. So this is what we are going to discuss on this. So these things are we have created with a small folder, RISC-V processor folder. So here I just want to show you this. So these are the main blocks of this main CPU RISC file, and right. So these are the main files for the RTL code. So ALU.B and your control. So these are the some other part like ALU RISC processor control unit, data memory unit, and the RISC test bench. You can see this. So the entire ALU module is a 32-bit ALU just designed. So this 32-bit ALU will be,
Excuse me, Navneet.
yeah,
Again,
yeah,
again,
again. Okay,
flow.
one minute,
It's
1 minute.
showing the flow chart. RTL to
Okay,
GDS to.
okay. Can see now. I think code is available right now, I think.
No, not.
Now you can see the code, right? Actually, I'm working with the app. Can you able to see the code, Shiva?
Yes, sir. Now we are able to see the code.
Yeah. So here we have a 32-bit ALU we have used with the different operations we have used. So to operate that ALU, we need a ALU main module and the data memory module. Only two things for this, uh, right? Your memory main process, that is your ALU process, right? So the next one will be, you can see this, the top module of the ALU, right? AB 32-bit as I mentioned with the same operating system. So with the basic arithmetic operations and the logical operations. CPU underscore top. So this is the top module, CPU underscore top module. So where we are start instantiating, you can see here. So there is a memory, instruction memory will be there, right? So this is a one module to operate in this. Then we have a ALU module to perform some ALU operation. Then for your data memory operation, then data reader, right? Data memory module, then your data read module. Then we have same like register memory and data memory also added in the top module. Right, so the slow.lib and the fast.lib, that is our technology library file, liberty file. We'll see what are the inputs and outputs are required for synthesis state. So that time we need our RTL code and the technology library file and the input. I think hope in the last session, one of our colleague has discussed. So data memory will be assigned. So then we have a program counter. So the data register will be registered with the help of the dynamic computer. Right. So these are the basic codes. I'm going to use it in my logic. Other than that, some codes are there. That is purely confidential one, right? So now we'll move on to the tool side. Raju, can you able to see the screen completely? Sure. So complete screen is visible.
Yeah. No, but it's showing flowchart again.
They just
Yeah. Now it's fine.
It's fine. Can you able to see the terminal window?
Yes.
Can you able to see the terminal window?
Yes.
Okay. Okay. So I'm running with the application only. I'm running. So what I'll do, so this complete code as we mentioned, so ALU module and the ALU RISC module, then your data memory module, then instruction memory module, then your register file module, then your RISC processor test bench module. So these are the main modules in the initial first step, right? So during this, right? So from here, I'm going to take a terminal here, right? So first I'll do this ESH and source. So source, home, install, and CSHRC. So where all your softwares are installed on the machine, and the installed location has been shared in this file, right? So once you enter, you can see this welcome to Cadence toolshoot. Once the license is also activated, either it is in the local server or in the cloud server, right? Then you can see this. The first one is for NC launch. For the first time, you can use NC launch -new. Right. So this is the first step for in the flow, entire flow. So we starts with this NC launch, that is your simulator, that is your incisive simulator. The recent version will be your Exilium simulator we are using. So as I mentioned, first we will create the library. Right. So first we'll create this databases and all. So once it is got created, we'll create this cds.lib file. So once your IEEE is not transferred, our worklib file also created. So here you can see all the files are here, right? Including the sub modules, everything will be there. So we'll run with the top module. You can see here you have two files. All these files got nagged. So for this, can see we can compile. So initially the first simulation process consists of three steps. So compilation. So if any errors are there, it will display in the downside module. So compiler. I can do this by clicking this shortcut, and the three also it's working. Right. So we need a test bench to check over this. So as it which data memory, instruction memory, all these things will. So here what they are right. So your files are there. Once it is start compiling with the register file, right? Right. Once the compilation is got over, then second thing is get events at the. So here first we'll do this compilation, then eject your elaboration. Yeah, it's moving. So here we can do this elaboration process for all the modules. You need to compile it properly. So one by one we can compile and register file also. You can do it. One by one it is not compiled. Then here you can see that test bench task module should be elaborated for the waveform. Okay. So more than one way. You can delete this. So we'll start with the compilation. First module. Then we can go for the second module, third module, fourth module, and fifth module wise. So module wise we can do it. Then we have this collaboration. Time scale is directive. More than modules. TB test bench. Right. So updated. That is one. So otherwise we'll go with the command mode and directly forward. So we can go with the iron ALU underscore restart v, risk underscore test bench dot v, RWC hyphen GUI. So where's timescale directive is missing on our more modules. So the compilation process was so iron ALU underscore restart v, then response underscore TV access plus RWC hyphen GUI. So it will start, keep on working. Right, we got this simulation. So TB can apply to the waveform. So where we can able to see this, and we can run the simulation for the entire command. So initially the test bench is running far behind. So but the operation will be only one data we are processing here, and they can see the data here. So after this, your A data is processed with the register 132-bit A and B will be there, reset signal. So 32-bit A and B, and your program counter starts keep on increasing 0, 1, 2, 3, 4, 5. Then your memory address. So here we have a different address 00A and 014 and 00, and data out for data, right? 00 and 00A, and here again it is 0 and clock signal and halted signal. Right? This is your total overall ALU output. So this is get activated here. You can see that, right? So the data is transferring. Only the one data we have checked so that you can able to check it. So the equivalent portion, what is the GitLab netlist for this code, right? So for that, we'll use the tool called the Genus, and we are going to discuss on a script file. So this script file is loading for the 45 nanometer technology file. So you can see here set underscore db, we are loading the 45 nanometer slow.lib file, that is your timing liberty file, and also we are loading the left file for the physical structure. To get the exact area and power analysis, we can add this left file. Then we have a generic process, right? Syn underscore generic, then synthesis underscore opt, that is for optimization. So these are the three steps. Synthesis is processing. So syn underscore generic, then syn underscore map, and syn underscore opt. So in this three method, your ALU netlist will get generated. That is your RISC processor ALU netlist will get generated. And for this, what is the what is the net output constraint file for the physical design? For the physical design, what are the files? It will take it as a input file and the input to the design. So that's what we are explaining here, so that you can see the different tools. Then we have the PPA analysis. You can see here, right? So these are the steps. So initially we are loading the inputs at the input stage. And this is our input stage. We are loading all the inputs. And this is our synthesis stage. We are doing 3 stages of synthesis. And this is your output storage portion. And finally your reports section. So all together will complete the process and your results will be readily available. Okay. Source your script file, that is your run.pcl. So if you run on it, so it will take your libraries, then it will do the initial generic conversion process, then it will start with the Gemini, right? So GUI window you will get up here, global and mapping. So around almost 194 cells are there. You can able to see here in the schematic. We have 194 modules are there. So here the entire module is depends, right? So this is the 3D view, means it's a 2D view, so we can't able to see the 3D structure. So we can able to see the front end here, and another portion will be there in the left hand side, right? So, right, right. So this is your net list. We got it with the 194 cells are there. So for this 194 cells, what is your gate count and your entire data length will be there. Okay. Right. So reports summary or gate count will get it. I think I'm getting here, right? Total overall summary you can see here for 194 cells. We'll get the net area will be 377. The total area will be 1062.97. So this is the distribution will be there. So in the report summary, if you see, so the entire cell area for 194 will be 685.924. Right. So this is the area and power and levels are there, right? And here you can able to see the power distribution power it is get distributed, the detailed power. So the entire module has been redistributed into module to module, and J1, right, J1 to J2 cells view. So the thing will be helpful, right? So this final data will be helpful in the power details, right? Power details are the power report, and the timing report. If you want to go and see the timing and give the value, and you can get it the values. Your default it will show as your source, that is your slack value, that is your source value checking only. So slack hold slack will get enabled after only the physical design is happen, right? So now your logical design uh, uh, right. So these are the details which is available at the unit initial level. So area report is important, then your power report, then your timing report. So these are the main three parameters we are including in the synthesis stage. So once your synthesis is completed, then we are going for the implementation section. Right. So then your next one is your physical design portion, where we can able to see the physical design activities, how it is get modified. So to do this physical design, we need for time being, we are adding the through script file. So tell that view, and this one is added. Right, you can see here we have. So the entire process has been added here. You can see the same 45 nanometer, but instead of that, instead of SIG underscore left dot LEF, left dot LEF, right? So this is your complete Innovus implementation system for the physical design, and here we can load it initial data. So through the script, you can able to load it. You can see first you have to load your design file. So you can add this default view. Right. So here we are start loading this. Load your first file, your global file. This is your global distribution file. We call it as global files. Then the next one default view will be there. Then here you have the left library. First one is your netlist, then your physical library, then your power modules, then your default networks will be added here. So by putting all together, I can get to see the design. It is added. Right. So this view file This is your left library and this is your netlist file. So these two things are added along with your VDD and your VSS. Okay. So here, so while loading the file, we need to load your defaulted globals. Right. It is loaded all these things, then give OK. So now once your load, your design is imported, right? Now you can see that the entire core list, right? The core of the net list, you can able to, right? There is another team, right? Right. So this is your main core area of the IC. So this can be done with the floor plan by two ways. One is the core based floor plan, another one is the pad based. That is your IO pad, input output pad based floor plan. We can able to do it. But that power pin based floor plan will take higher time to do the actual IC. So the higher IC will be right. So now we'll go for this floor plan, specified floor plan. And here the entire aspect ratio will be 1 for both your height and width value. Both your height and width value we are adding. So your core utilization will be 0.7. Then your core to die boundary, I'll keep it as 8 micrometer between within, right? So within the floor plan view. So the central square will be the central floor plan. For the silicon area will be defined into multiple rectangles. So there is no gap between one terminal to another terminal, right? So this everything is determined, right? So then power planning, power strips, right? So the external power supply is given from the right, which is nothing but your power plan. Right. So power plan, add string. Then we can add this VDD and VSS. I think most of the steps are same like what Raju did in the morning. So here it is metal 9Y. Here it is metal 9Y. Sorry, left one. Left one will be metal 2AV. Yeah. Right, update your so metal 2 will be added here instead. Just a minute. Power planning, add ring. So 8V will be there. Update it and you can apply here. You will get it metal 9. So metal 9 over for horizontal layer, metal 8 for vertical layer. Then for power plant between the monitor, how many monitors are going to add it? Uh, okay, so power planning add ring. So power stripes. So in this case, horizontal, we can choose it as metal 9 and update and also add your VDD and VSS. Right? That is a pre-layout analysis. So after this ring power, sorry, got little get struck. So after VDD metal 9 horizontal, so it is update and here we can use the number of stripes 3. You can apply, you can update it. You can see here in the center of your core area has been added with the 3 stripes. And we can choose vertical and metal 8 has been replaced, right? Okay. And go for the power rails. So these power rails are mandatory. So through this power rail only, standard cells or macros will receive the supply. So macros will receive the supply from stripes, but actually students will receive after the end cap cells. Right now, we can go for the placement menu. So physical cell handicap will be very added as a pre-cap cell and your post-cap cell select also we are accessing as a post-cap cell. Right, by adding this you can add the well tabs here. You can able to see the well tabs are added perfectly. So within this entire rectangle period, you can see this. Every one layer there is a one VDD at the top and VSS at the ground. So this will really place the standard cells with respect to the place IO. I O. P. N. S. Opens. And then okay. And then okay. So now after this, various iterations of algorithms. You can see iteration 1, iteration 2, iteration 3 will be there. So after the various iterations of, so iteration 1 and 2, how many cycles are run? Okay. So 6 iteration we have run. So finally you can able to see the netlist, replaced netlist you can able to see in this. So by removing this, by removing the layer, you can able to see the entire netlist, right? So each netlist having their own IO pins and their IO paths. Right, so this is your player's cell. And for the clock tree synthesis, next thing. So for doing clock tree synthesis, we will use it for 45 nanometer technology file, right? So your clock signals should get add with the NDR rule. So here you can see that at this edit option, we have the NDR rule will be there. So the NDR rule says that the width and spacing of the metal layers over various metals should be double. You can see here metal 1 will be 0.06. Here metal layer metal 1 will be 0.12. The same value for metal 2, metal 3, metal 4. Exactly double the value will be. Right, and the spacing also you can see here spacing also 0.06 and 0.07 will be there. So here spacing you can 6.06 as 0.12 and 0.07 will be act as 0.14. So we are naming this value as 2W2S, and for the clock root we are using the metal layers of metal 5 and metal 6. Right, metal 5 we are using and metal 6 you are using. Right, this is particularly for the clock routing, and later this we are adding the clock tree, right? Clock tree type this trace value to the trunk and leaf. Right, this trunk and leaf is going to add a buffer. Right, buffers we are adding clock buffers, then clock inverters we are adding, then clock inverters 6 and 8 different clock buffers and the clock inverters are added. Right, then your clock gating also we are used. Yeah, yes, clock gating, right? Then we have the generator. Right, sorry. Okay, this you can get it here. So after these, all these files has been updated, you can close this file. So NDR also it is doubled the value, that is the main thing, so that we can able to see this checking. So we are running source run.tcl left library is sorry. So now we are running the CTS, so source cts.tcl will be there, which is the tool command language we are running. So here you can able to see this. Let's run the value. Now if you go for this graphical user clock router uh, right, so clock tree distribution. So here you can able to see at a different time interval we have a different clock they are giving their own clock vector, right? So this you can able to optimize by applying the uniform distribution. Right. So previously it was randomly it is allocated. Now the randomly allocated, that is randomly received clock signals will be changed as uniformly it is distributed, and now it is hanging is not there. Right. So the server CTS process, then your routing. So close it and route menu, special route. Right. So this you can able to add. Right. Your place net list and equivalent to your layout, everything will be added. So now the next thing is your routing. So after your routing algorithm, tolerators. So this will be there. Enable with the routing layers. So now we can observe the thing that I can see here via gen created 0 via proceed 0 via avoid calculation. So if any violations has occurred and due to the violation, it will ask for the next files to be downloaded or not. Right. So the design is routed for time being. This is your floor plan view, amoeba view, and the cell view will be there. So that will be input outputs will be there. And see this post route and post CTS, both are the same, right? These two things are the same. So once this is done, right? Your routing is done. You can able to observe the interconnection wires in the layouts, and in the layers also you can able to see, right? So for going further timing, You can able to analyze your timing post-truth. So post-truth for more than half second, nets are routed. So after this routing, so initially we'll do with the post-truth setup violation checkings. So after this routing, nano route is completed, timing, debug timing. Now we are running with the setup. So with this setup, we have no violations as of now for the timing. So because we are using the timing as 1 nanosecond, right? So 1 nanosecond in the sense we used as one micro, that is 100 micro signals, 1 by 1 nanosecond, right? 1 microhertz, that is our 1 hertz signal we are using. For this equivalent constraint, you can see this report has been generated. So total 73 paths, out of that there is no violations. So that is what it shows here. So total 73 violation paths. So total 73 violations occurs. That means there is no Nash for. So the setup file has been replaced by hold. So hold also, as of now we don't have violations for 64 to 64 operations. So different timing paths have their different slack values. With you can see, you can say with the local staff access to staff access right. So this staff access does not have a counter defined, right? So this counter design will be available in all the modules. So the next one we are running. Right, so both the timing side there is no violations. So violations are made here, right? So there is no more violations. So we can add it. Suppose if any violations are there, we can optimize through optimizations. So optimizations will be CCO, optimized design will be there. So which stage you are getting error, so you can choose it accordingly, whether it is setup or hold. So based on that, you can optimize it. So it will get optimized and it will try to reduce the commits. So these are the one files, and for timing analysis, right? For timing analysis, uh, if you want to detail, we can go further for the tempest and we can get it back the updated database here. Okay, so this is your timing, and you can, if you want to extract RC, you can extract it by using this spec file, and you can do it. Right, and the same way, if you want, you can write your SDF file also. Right, and you can save the database file, save design, GPU, .enc will be the database for saving the file. And same, you can save the netlist file, save and netlist. So this netlist, you can save it as physical netlist. So I call it as a physical netlist for doing the post layout simulation. Okay. So the same thing, we'll take a post layout, that is our back annotation. For doing this back annotation, can use it where we used our iron, right? Instead of ALU, your top module, Verilog module, we can use your ALU underscore physical netlist. So physical top underscore ALU underscore top iron ALU underscore, sorry, not ALU, it is iron CPU underscore router underscore physical netlist dot p. So along with that, we need a slow dot b file. Then your RISC test bench same file. Then we need a 45 nanometer slow dot b file is required. So for that, you can take it from this. Yes, slow dot b file. So you can run along with that slow.v file, then hyphen access, so wc hyphen qi. So in this physical netlist, we can add that. One nanosecond by 1 nanosecond, you can use it. Top module on the test bench. Let's finish. Okay, the waveform starts beginning. Almost at the last stage, once this is satisfied, your waveform will satisfy your initial output. So this is the output we are getting from the layout. So this layout will be there. So which is the output you can see here. So what is the output we got it from in the initial stage? The same output we are getting from the layout also. So the layout here, whatever we have drawn is correct. So that we can go for generating the GDS/OSS output file. So here you can go with that CPU.gd, yes, and the stream out will be your physical verification 45 nanometer. Stream map file will be there. Then stream out. So that you can able to see your CPU.gds files. So this is your pad base, that is your core based physical design. So still the final stage will get completed by the IO, that is pad based physical design, so that the final sign off process will get completed. So for the time being, you can understand this one. I think hope everyone have understand this flow and the setup. Okay. So any questions? Any questions from the participants?
Participants, if you have any questions, you can unmute yourself and you can ask, or else you can drop it in the chat box too.
Yes, ma'am. Yes. Thank you. Yeah.
Sir, if any of the participants asked to share your contact mail ID, can I, sir, for reference?
Ma'am?
If the participants asked to share your mail ID for future reference, can I share, sir?
Yes, ma'am. Yes, ma'am. Or otherwise, we can share personal mail ID, or we can. I'll drop in the chat box, ma'am. We have a
Sure,
Cadence
sir.
Cadence.support at Entuple.com. For any further any queries about our Cadence tools related, or anything about tools related issue, or any details, if you want, you can contact this mail ID. That is cadence.support at Entuple.com.
Thank you so much, sir, for sharing your expertise among us.
Yes, thank you, ma'am.
And now I invite Ms. Sindhil Priya to deliver vote of thanks for this session. Over to Sindhil Priya.
So good evening, everyone. On behalf of R.M.D. Engineering College and Department of Electronics and Communication Engineering, I would like to express our sincere gratitude to our distinguished resource person, Mr.V.Navaneethakrishnan, Senior Application Engineer at Entuple Technology Private Limited, for delivering such an insightful and technically enriching session on ASIC design and implementation of RISC-V based processor using Cadence tool. Sir, your detailed explanation on RISC-V architecture and ASIC design flow using Cadence tool has given our participants a deeper understanding of real-world design methodologies. We truly appreciate the time and effort you have taken to share your knowledge and the practical experience with us. Thank you once again, sir, for your valuable contribution. Thank you, sir.
Thank you, ma'am.